So let me quickly start the slideshow. Slide, which you had seen already, this gravitational redshift. Well, in order to come from this formula to this formula, there are a couple of mathematical interpretations necessary. We cannot only, unfortunately, enter this classical potential energy. Yet it can be shown this is the case. And experimentally, if you want to check this, this is known as the Repka-Pound experiment or the Harvard Tower experiment. It's the same experiment, just different names. And they use the Repka and Pound used a tower of only 23.5 meters. And they could show using a technique called Mössbauer effect. This is really the case, this gravitational redshift. So, very fine measurement, very precise. Okay. And hopefully you have seen this film with the black hole eating the Earth. Obviously, it wasn't the case. Well, that's typical when the media gets something to make a paranoia. Then any farmer in Wisconsin needs to lawsuit CERN. And for any strange reason, CERN went for this because CERN has diplomatic immunity. So this is an extraterritorial organization. And if you work for CERN, you get usually you can apply for diplomatic number plate. And you're paid like hell, tax-free. So I've hopefully seen this video. What I recommend you is stop this video at some point, but then have a look into it here. This one got a Nobel Prize. What you see is basically the zoom in into the center of our galaxy, which is again southern hemisphere. And then in the center of the galaxy, there was a video made for a couple of years. Basically, you take occasion every couple of days a shot, take a picture, and then you make them together as a video. 2 years ago, this got the Nobel Prize for. So what you see is the moving stars moving around the comet's center of gravity, and occasionally you will see that one of them speeds up and then slows down again. This is when it's ellipsoidal orbit, when it comes close towards the supermassive black hole that is in one of the foci. Then it accelerates until the point of closest approach, and then when it moves away further away, it slows down again. And this movement, if one then makes the orbits, one can find this common center of gravity, which must be about 4 million suns. So clearly there is something we can't see, but it interacts via gravity. Well, this is one way to observe it, by the gravitational interaction of towards other stuff. The next way to observe black holes is if they would fly between us and the light source. The massive gravity would again distort space-time, and we would get this gravitational lensing effects. As we have seen in the third or fourth lecture. So this is here nicely shown in this second film, basically showing Einstein, a picture of Einstein, and then a black hole going in between us and Einstein, and what that will happen to this picture. So the true Einstein ring. Oh, the next, so hopefully when you have then seen these videos, we can see them when they feast. What happens if an object comes very close, very close? By the way, to get rid of a myth, if we would replace our sun with a black hole of the same mass, what would happen to the Earth's orbit? Would it eat the Earth? What counts there is the distance between the two objects. And this stays between the center of the black hole and the Earth stays constant. The mass stays constant, so the gravitational force at the position of the Earth remains the same. All that happens, it becomes dark and cold. So they are not the super all-eating monster. It's just when you come too close to them, when you come close to the event horizon, then you get these massive potential energy differences. That means the force down here, and the force is basically in this potential energy diagrams, the derivative of the potential, what means the gradient. And if you make the gradient up here, it's of course much flatter than down here. So if you make their tangent on this curve, it's obviously quite a difference. It means down here the force is much, which is the force is the gradient of the potential, negative gradient of the potential energy. You have at the feet a much higher force than at the top. What means this? There's a force difference. This case caused that here the acceleration, mass multiplied with acceleration, is the force, is much higher than up here. And what you get is it's so-called spaghettification of an object. So it will be ripped apart. That is one thing. So if an object comes close to a black hole, it will be ripped apart. Okay, if it's ripped apart, what will happen? Again, it cannot directly fall into the black hole because it usually came along with a different velocity and it would have had a distance of closest approach, what means there's some angular momentum in the system. Again, the stuff gets ripped apart, but then it needs to spiral around the black hole. And in this spiral process, of course, it gets accelerated. In general, this means it's already, if it's some kind of star, it would be, gets ripped apart, the plasma gets accelerated, becomes hot, it starts, there are collisions between the plasma particles, which make it probably shine. So suddenly we see, then we have, of course, this plane again. The collisions cause that some go closer and some go further away. We get a disk, an accretion disk. While the black hole feast, it creates this accretion disk again, angular momentum coupling. And some stuff might at some point end up on the event horizon and get swallowed. Black holes grow, eats and grows. Some stuff might be so much accelerated that it basically can escape. But most of the star will be eaten. So this is basically the angular momentum will again cause accretions. Of course, then they have a plasma orbiting very fast around. You create massive magnetic fields, and then occasionally some charged particle might be again accelerated away. In this magnetic field lines, trapped, this creates again jets, so standard almost. And if you want to see what happens if a star eats, if a black hole eats a star, it's nicely shown in this film. So just make a stop and take a look at this and Well, I can't say enjoy it, just be. I was blown away. And a couple of years ago, an X-ray telescope has observed such an event in a nearby galaxy. So this occasionally happens. And later we're going to talk about what is called quasars, quasi-stellar, distant quasi-stellar objects, which turn out to be center of galaxies, supermassive black holes. And when they feed, they basically shine for a short while. Stop it. Okay, so another source of high energy light, again, X-ray gamma rays. Another option to create these type of bursts. Well, if we could make a picture, it's probably something that we would see here. We have, of course, the accretion disk. If there is some gas that is hot and starts emitting light before it reaches the event horizon. So this must have been X-ray or gamma rays. Then the redshift, we would appear it as visible light or infrared if you could see the infrared. And then we probably would see something that looks like there is a second accretion disk, and this is basically light from behind that is bent in this curved space around. This is the light that would be in the disk behind, and from above and below. That appears, that comes slow out. So, and the object itself, everything that is beyond the event horizon, that's it. This time is basically coming to a standstill, almost standstill, and then the waves are, the space is so expanded that there are no waves anymore. So, and the accretion disk is here deformed because the geometry around the black hole is so alterated. So this is an artist impression a couple of years ago. I think most of you have seen this by this Katie Bowman. This picture, how she had this once in a lifetime moment. Thereafter, terabytes of data taken with loads of infrared, mostly infrared, radio telescopes and whatever. Of the, I think it's the galaxy M87, Messier 87. There the center. And what she's here on her laptop. Basically the picture that she was one of the first people to see. This picture here, once in a lifetime moment. And after, don't know how much work and suddenly you see the final result. Even it doesn't look so spectacular at first, but again, what you see is basically the accretion disk, and here you wouldn't see anything except the light is spent around. The same is true for, that's why it's here often so bright. Because the light also from behind is again also bent and appears together with the light from the front. So this is the work of the Event Horizon Telescope collaboration, that what you see in here. This is basically the black hole. In the center of this M87 galaxy, and this will have again a couple of million solar masses, this black hole. So we can now see them directly. So another way to see them nowadays directly, well, what happens? Space-time changes. And every time you have a change, it communicates with the environment via waves. These terms then, with space-time changes, gravitational waves. And we had this already, this gravitational event from That must be this 2015 one, if it's published, or 2016. We have the inspiral linked to masses, and at some point they merge. The slide of the ring down. That's it. And we get basically this. What we observe is the gravitational energy that, when they come closer and closer, that is irradiated while they do so. So we had there directly the chance to observe it. We would have expected usually a black hole, either the supermassive ones in the center of galaxies or a couple of solar masses. Here, the big surprise was this intermediate masses of 36 and 229 solar masses, and then the outgoing one is 62 and 3 solar masses, basically transformed in order to deform space. Strange thing. Well, again, this would be a video if you want to see it again, how they were observed, how they basically how the gravitational waves are really detected. If you want, if not, then just go on. So we have now a couple of chances to see it. Really, this is predictions by general theory of relativity. So these are tests of a theory of relativity at the absolute extremes. And it turns out Einstein was again right. Okay, so this is now one thing. We have black holes. We can indirectly, or that occasion nowadays, it's still indirectly if you have the heating of gas, and so still, of course, there is nothing there. Is the absence of something already proof of its existence? It becomes philosophical. It's now a question. Once they're basically all eating monsters, and then they grow and grow and grow and grow. So one would assume they become bigger and bigger and bigger. And that's it. At some point, they have eaten everything, and then they are there forever. That's not exactly true. So are black holes eternal? And the answer has been given by Stephen Hawking, who used the laws of quantum mechanics to define what is called Hawking radiation. Well, in quantum mechanics, we have this energy time uncertainty. That's basically similar to Heisenberg's uncertainty relation, that we can never measure time exactly and energy exactly together. In mass, you're going to learn that frequency, what means quantum mechanically, the energy, and time are conjugated variable. When you do Fourier transformation from time to, then you will end up in the frequency domain, therefore in the energy domain. And vice versa if you go the way back. It's the same as when you do from space. You will end up with a variable k, which is the wave number, 2 pi over the wavelengths. But these are also conjugated. In quantum mechanics, it turns out that the momentum is h bar, or Planck's constant divided by 2 pi, or h over lambda. Momentum and space are related. Things that you're going to learn, and for these quantities, we can then define what is called uncertainty relation. They cannot be measured exactly together. So if you make very precise time measurement, usually the problem is that your energy measurement becomes very diffuse. Oh, this is inherent in the stuff. And here, this energy time uncertainty tells us now that for short time, it can change, and energy is not really defined in the system. It means for small time, a particle doesn't know what energy it has. Uh-oh. So, or for short time, energy conservation is violated. This has as consequence, for short time, there can be enough energy there in the vacuum, enough energy there for very short time that corresponds to the creation of particle and antiparticle in mass. So if you have 2 times the rest mass energy, that's delta E. We could calculate now what is the delta T. And in this short time, this particle and antiparticle spring into existence. Here they start. And after a short time, you know, multiply this with the speed of light and we get a certain distance. They meet again and cease to exist. And after this short time, the energy conservation is again fine. There was no energy in the beginning, there's no energy at the end. This has been experimentally again proved. We take 2 capacitor plates. In vacuum. Now you have outside, right and left of it, you have particles jumping into existence, and inside. But inside there are less because you have a confined, this limits the number of wavelengths that you can have. The boundary conditions multiplied with n times the half the wavelength, that limits the number of particles that you can create, while outside you can create much more. So now you have much more particles. This means the chance that one of them hammers against from the outside is higher than from the inside. And the capacitor plates will at some point move together. That's the Casimir effect, experimentally shown. So the vacuum is not empty. If you go and tell this to somebody, it probably will send you to an asylum. Constantly particles and antiparticles are created from nothing and vanish into nothing. Oh, one of these things you accept. I don't think that people can really understand this. We call this virtual pair creation. The pair that is there, but it's after a very, very short time, it vanishes again. If you have recently heard about this magnetic moment of the muon, that it was so deviating from the theory value. It's not exactly true. They have experimentally measured something and compared to a previous calculated theoretical value. Now, the previous calculated theoretical value included interactions with particles, with some virtual particles that are created and vanish immediately in the surrounding of this muon. This is heavy brother of the electron. But then they made a cutoff. At a certain mass, they said, okay, we change this, or we don't consider this anymore. And now, the next value was then after the measurement, people started to calculate to higher and higher masses. And now the theoretical and experimental values start to agree more and more. So this again is strong experimental evidence that this virtual pair creation constantly happens. Space is not empty. Vacuum is not empty. Oh, and now Hawking basically said what happens if this virtual pair creation basically happens on the event horizon. So on the Schwarzschild radius. And one particle is basically trapped inside, the other particle might have enough energy to escape. So suddenly we have this virtual particle, at least one of them, come into existence. When it escapes, of course, it needs to have quite a high kinetic energy. Makes the process unlikely, but given enough time or given enough chances, how likely is it to win in the lottery? But still, every week, I would say at least one person wins because there are enough tickets bought. So if this happens, that one of these high energetic that can escape particles is created and its partner is still inside, this means somehow energy came into the universe. But it's not coming from nothing. Somewhere it must have come from, and it's taken from the mass of the black hole. It means the black hole is now undertaking a diet. It's shrinking. So black holes can also shrink. Given they don't feast, they don't have anything to eat anymore. So even when they eat, there can still this happen. But of course, then if the intake is higher than the out giving away, you grow. If you eat more calories than you consume via sport or thinking, then you grow. If the intake of calories is less than the outgoing one, here now via these virtual particles that turn into real particles. So in the moment we can observe it because the partner is missing and cannot annihilate anymore. We would talk about the real particle. The black hole shrinks. It's something you now probably have to digest mentally, but it happens. So this virtual pair creation, given enough time, there's no, it doesn't have anything to feast, and given enough time, the black hole shrinks, it shrinks, it shrinks, and at some point might cease to exist. Not even they are eternal. We have the space filled again with this Hawking radiation. Now in this process, very likely we create the same amount of particles as antiparticles. If they meet, what will they do? Particle, antiparticle, if they meet, they annihilate and create another radiation. Usually quite high energetic, so gamma ray. But then we let space continue to expand. We shift it, we get a redshift, and at some point we get another microwave background. But this is in such a distant future. No, do I care? And with this, I could say that's enough for these monstrous particles or monstrous bodies. Well, next week we take another look at the supermassive black holes. But then rather as the role in the center of galaxies. So next week we are going mostly towards our galaxies. With this, I would say, thank you again for your attention, and hopefully you stayed all the videos all the way until now. See you then in the weekly class test.